My name is Emily Kilian. I'm a principal engineer for the Microsoft Azure Storage team. More specifically, I'm the tech lead for the disks team. The disk team owns two products. It owns, if you make a VM in Azure Storage, you need a disk to host that operating system. We provide all of those. As an example, we also own the SAN product, which is a newer product and is going to be the topic of today's discussion. If you see in the brochure, this was supposed to also include my product manager counterpart, Yumin. She wasn't able to make it. For good or for bad, as a result, this will be a much deeper technical dive. So we're going to do a couple slides on the product and get into what SAN is, but then we're going to have a much lengthier section on how it was created. And then at the end, we'll get to iSCSI, and if we have time, a little bit about NVMe over TCP and how we're looking at implementing those. All right, so Elasticsearch overview, that's going to be the more product slides. Then I'm going to actually step back a second and talk about Azure Storage architecture as a whole. This will not be specific to disks, but actually just Azure Storage generally, whether it's block storage, object storage, or files. We have actually a pretty similar architecture across these. Then we'll do a deeper dive into how we created the product within this architecture, and then finally, this iSCSI protocol content. All right, so first, SAN. This is a conference with a lot of folks that have been in storage a long time. I'm guessing many of you know already what a SAN is, so I'm not going to really harp on this. Our SAN looks a lot like an on-premises SAN. So you get a whole bunch of volumes, right? You have a very similar management experience. There's kind of three layers. You provision the SAN, you have volume groups, and then you make volumes within them. The main sell here is rather than managing individual disks for each of your workloads, I mentioned VMs as an example earlier, and spinning up a whole bunch of those and then thinking about what size exactly do each of these need to be. You can save time and money with the cloud native SAN. So this allows basically the provisioning, scaling, access management, all that redundancy is going to be kind of managed and purchased as a unit. We also support industry standard protocol iSCSI for data access. All right, so this is three layers. I'll have one slide for each, so we'll start with SAN. So this is your provisioning unit. You're going to go in the Azure portal, and you're going to say, I want a SAN. This is a couple clicks. So this is a very simplified process. You get two choices. There's a base SAN. This is groups together. Basically, you can get a bunch of sizes. That size comes with a fixed number of IOPS, because IOPS has to scale with size to a degree. You can also add on capacity only units, and that's quite a bit cheaper. So basically, you're going to get a pile of IOPS and then some amount of storage. And we're going to bill on the provision storage that you make as that SAN for capacity and for performance. You can also delete it all as a unit. All right, within that SAN, you're going to make volume groups. Volume groups are kind of your unit of management. So those are going to be for applying security, encryption, data protection configurations, all of that sort of stuff. So for example, we do a lot of network security. If you want to decide what VNet can access the various volume groups, you're going to set that up at the volume group level. Then, we're basically, you can have some number of volume groups. This is also where you can do encryption settings. When I say encryption, I don't mean network encryption. I'm talking about encryption on the disk. If you want to make a custom key for that you can rotate and manage, you do it at this particular layer. Finally, volume. This is where we're getting into the good parts, and this will be most of what we talk about for the rest. This is your actual, disk that you're going to mount. Read-write access over SCSI, create, delete, that's the stuff that you're actually going to do as a management plane, and then, dynamic pooling, provision, performance targets. All right, so I hope you guys all have the natural question, why did the cloud make a SAN? It's a great question, right? And if you didn't ask that, you should have. So I'm going to talk about that. So I mentioned before, we offer VMs, right? And we do listen to our customers, and customers have two problems with that. So VMs have this, if you have a very stable, basically amount of IOPS that you're going to need, it's very easy to get one of these and spin it up. The problem comes when you have a whole bunch of VMs and they have these spiky workloads. You have to buy for the very top of what that VM is going to have to do, and that can be expensive, difficult to manage, and difficult to provision for. So what SAN allows you to do is basically provision every disk at kind of what you expect it to use, and then get a little bit more. And as long as all your disks aren't spiking at the same time, this is much more cost effective. There's also management overhead. While disks can be put in things like resource groups, these are lighter weight. They're kind of an abstraction at a next layer up. And the volume groups are actually a much tighter unit of control. So that's from the disk perspective. The other thing is we didn't support iSCSI before. While iSCSI is an old protocol, SCSI is from the 80s, iSCSI is from the 90s. I was born in the 90s. This protocol is, my age. It still has ubiquitous support, right? Windows, Linux, lots of people are still using this protocol. So it's something, where we'll start with this. We have the opportunity to extend to more, but it's actually a pretty good protocol. I like iSCSI, and we'll talk about that a bit more later. This also allows us, surprisingly while SAN feels older, we've actually found that a lot of the primitives for SAN are good for a lot of newer products. Azure VMware is more traditional SAN, but container storage. We did a presentation at SDC on this, I think, 2 years ago, and container storage actually needs a lot of the same primitives of a SAN. You want to make this big unit of storage, and you want to quickly create and delete pods or pod storage from that particular unit. And the primitives we had already didn't work as cleanly for that. So what we're actually doing with the SAN is supporting container storage of all things. So what is old is new again with this sort of thing. So if you want to learn more about that, there's a presentation from SDC 23. I've copied a couple slides from that, but you can get a little bit more detail on that. All right. This is my favorite part. We're going to step back a second, and we're going to do a brief history of Azure Storage. All right, 2010, this is when Azure originally is designed as an app engine, and it is imagined to be an object storage platform. There is no thought on that this is eventually going to be IaaS or have file storage. It's designed really for that particular use case. Azure implements blobs with the REST API. We have some client libraries. I was hired out of college to work on those client libraries, so this is where I entered the picture. And then eventually we realized, hey, VMs is going to be a huge part of the cloud. And we need to support block storage. Eventually to 2015, file storage, SMB, NFS, REST-based access. We have a lot of folks here from Azure that are on the SMB team, so if any of you guys work on that, you can find some great folks to talk to here. Finally, et cetera, I'm obviously glossing over a whole lot here. We get to 2023 and the SAN block storage. So why am I telling you all of this? This is a discussion about SAN and iSCSI. This architecture diagram is from a 2011 presentation. I've changed virtually nothing other than adding the SLB because that's something that was there before and just missing. This particular architecture, we've used all of these years for all of these products. And I know that sounds absolutely crazy to storage people, maybe not to other people, but to storage people, because these are such different workloads. Block storage, file storage, object storage are just not very similar. So it's kind of amazing that we've gotten this to work. To be clear, it's not like we do the exact same thing for all of those. We've amended this to heck, right? And a lot of this presentation will be about how we amended it to work for SAN. But the general idea and the general layout of this has been the same since the very start of Azure Storage, and it probably will be there in 10 years. We have built more specialized stacks. I'll get into that a little bit later, but a lot of things, in storage start their life cycle in this particular environment. So this is a lot of boxes. I'm going to simplify it a little bit. Let's do a recap. So first, SLB. First, actually, on the very client side, you're going to use DNS to resolve which IP to go to. That IP is going to map to a particular storage cluster, and it's going to hit the SLB. The SLB is going to pick a completely random front end to serve you. Obviously, it uses health metrics. It's not going to pick things that are down, but otherwise random.
What does SLB stand for?
It's a load balancer. So the load balancer is going to pick a largely random front end. And this is how we spread things for that matter, load balancing. The front end is completely stateless. That's our protocol endpoint. That's where, in this case, iSCSI is going to be hosted. REST is hosted there. It does authentication, it does authorization, and it does a lot of the metrics and logging. It does a whole bunch of other stuff as well. But for the purpose of this conversation, it covers that. Next is our partition layer. That's the key value store. That's the database of this particular, portion of things. I'm going to get a little more detail on it later. But this kind of manages our data abstractions. The front end layer basically skins things. It's what makes it look to the customer like all these different protocols. But we actually have a very similar data storage in the partition layer. There's a couple specialized things for different protocols, but it's a relatively generic KV store. Finally, the stream layer, that's not something we had to modify for this particular project. That's our distributed file system, not a file system as in POSIX. This is an append-only system. This handles our replication, all of the persistence, EC, that sorts of things. Stream layer is very cool, just not the topic here. That probably deserves a presentation within itself. Well, we use like 20 terms internally. I'm being very careful to say cluster. We actually call it a tenant internally. Stamp is another one. I'm not certain the history of stamp. I can tell you for tenant and cluster where those come from. These are all basically the same terms. Internally, there's some differentiation of which is the software term and which is the hardware term. I don't know beyond that. Maybe because we stamped them down, at least at this point. Maybe not then. Okay. Why do we love this architecture so much? So this was designed initially for object storage, which needs excellent scale out. What we found out over time is that it's very flexible. I went over those 3 particular layers. We found it very easy to add new things to this architecture while maintaining the scale out. It's also very fault tolerant. That's partially because of the architecture that's covered deeply in the paper that was published on this. But it's also, we've battle tested this for the better part of 1 to 2 decades, and it is very stable. It has mature logging, metrics, diagnostics. People underplay that, but that in itself is a feature that has performance costs that is something you really need to run a service. And all of that is kind of already there, and when you add products to it, you get a very mature feature set and a mature base to build upon. And additionally, you get that excellent scale out, which is really in the end the sell of a cloud. Like I mentioned before, we have more specialized stacks. UltraDisk or Direct Drive presented in SDC 22. I was actually one of the original members of that team, so I know that stack deeply as well. That's a disk specialized stack. It's great. It's blazing fast. You get sub-millisecond latencies, closer to half a millisecond latencies on that sort of stack. It's not as flexible. So it's an excellent thing. It's an excellent thing you're going to want to use for disks, but it's much harder to add these newer protocols, and you're not going to get the sort of feature set that you do on the more traditional stack. So pros and cons. Great piece of software just for a different purpose. Okay, Azure Elastic SAN deep dive. Circling back around. All right, scaling. So Elastic SAN span a region. This is interesting in the cloud because most of the time when you have a particular object, or you have even a particular account, it's going to be on a particular cluster tenant stamp, to make the joke of terminology. But for SANs, you actually span all of the data centers that are within a region, and we can have quite a few. Azure, don't quote me on the exact numbers, but we have 70-ish regions and thousands of clusters kind of across those. So we are very large, and a region can contain quite a bit of underlying hardware. And SAN allows you to take advantage of all of that. Each volume is physically stored across a set of storage servers. So that is, connections are going to hit more than one FE. That's always true. But we also actually increased our scale out at the partition layer that was mentioned before. Usually and historically, objects are hosted by a particular partition. In our case, we were actually found ways to spread it across more than one. And as I mentioned before, each connection is going to hit by a different FE. So as a result, on a SAN, you can get millions of IOPS, double-digit gigabytes per second, and single-digit millisecond latencies.
So it's not bound by the storage account, like when they create the elastic.
So
in order to do that.
Nope. So there's no accounts involved here. Under the covers there are, just to be clear. We're building on a system, and we'll create them and manage those, and you can actually see them a little bit in the IQN, but we do those. So when you make a SAN and create a volume, we decide where to place it. We manage the account. We do all of that abstraction out. And that's part of the sell of why we have things like, when you create a VM, you also don't have a storage account. Under the covers, we kind of do some of that work for you. The point is to make something that's easy for people to actually manage, and so that's not something that we expose upwards.
Yeah, that's why I also use the critical speed of having a hotspot. Because at the beginning, you have a storage account that just would create the same name, so the hash would be very close.
I'll get into that later. We're actually doing we're doing hashing specifically to make sure that things are very well spread. So I will get into that. I'm going to give a very good answer to your question because it's one of the coolest things we did here. All right, so just for a review, I think a lot of this audience probably already knows how iSCSI works, but probably not everyone, so I'm just going to do a quick recap of how it works and how a request would flow through our system as well. So we're using iSCSI with MPIO, so that means multiple connections. How many connections you need depends on how much you're going to push. A lot of times we recommend about 8 per volume. As mentioned before, you're going to do a DNS resolution, you're going to get an IP, you're going to hit that SLB, and then you can basically start to kick off those connections. Important note for later, MPIO, there are multiple connections, and these connections are going to different front ends. They're not going to the same one. Every connection you spin up is going to be very well spread, and you can see that here where the connection 1 is not going to be on connection 2. For a particular request, we'll usually hit a particular partition server, but when you see multiple PDUs flowing here, different pieces of data are actually going to be on different partition servers. Those under the covers we'll call stream. I don't have that here because I ran out of space at the side of my diagram, but in the end it'll be persisted there as well. All right, so I'll start with the FE and then we'll get into the good answers on the scaling at the partition layer. So multi-protocol support. What we did here within the front end layer, we also have 3 layers. It's still one EXE, it's not running across separate pieces, but it's a multi-layer architecture. When you want to insert a new protocol, what you do is actually mess around with this protocol layer, and this is how we build flexibility into the FE itself. We're able to reuse a lot of code in the service and provider layer. The provider layer is a pretty simple wrapper around our lower layer abstractions, but more of the magic is in the service layer. That's where we put a lot of the business logic. I mentioned authentication, encryption, all of these features. Those are there for other accounts, and we can reuse most of that completely out of box, well tested, with an interface people understand by reusing this particular layer. It's not completely out of box. An engineer has to sit down, hook it up, test it end to end, all of that stuff, but it's pretty straightforward. All right, so quick review before we get into the partition layer. So how our partition layer works is it's split into range partitions based on load. So if you imagine it alphabetically, which this slide shows, you'll have a range A through H on one partition, H through R on another, R through Z on a different one. These are dynamic. We can split them, we can merge them, and we have the table master, which was that Paxos ring off on the side, is going to decide based on load how to do that. The thing here is, though, as was mentioned by the audience, right, is that there is, if you have a particular account container blob, if we're thinking object storage, or a particular disk, you're going to be on a particular partition, and you're going to hit scale limits there. We wanted to change that. There are cases actually already where we scale across more than one. We have some striped disks where we're going to go over a handful, but it's a handful, and we really wanted to get beyond that particular scale unit. So what did we do? We divided the volume into something called shards. You guys know RAID. This is very similar to RAID. It's just we have a lot more disks in the cloud. So this, rather than spreading across what you can plug into a machine, you're spreading across the hundreds that are going to be, in a cloud. So you can pick whatever kind of, internally, not you, the customer, but we internally, there's a wide variety of shard sizes, that we can choose from. It's, a gig right now or so. Don't hold me to that. That's an internal setting. But we basically divvy up that data. So if you're doing a relatively random workload, you're going to hit completely different, partition servers for each particular I/O. We've also added striping to this, so that, we have a very complicated math problem we'd have to show for how we, combine those particular two, but that's helped as well with sequential workloads. So shards are created on demand, and they're spread very evenly. They're distributed via hash. So we basically hash all the information and, about the offset and the name of this volume and that sort of stuff, and we put that at the very beginning, so that we have a wide spread across that kind of alphabetical range. A little more complicated than that, but that's the rough idea. So that's all good and well, but the problem here is the more you spread your data, the more problems you have with global state coordination. So you're going to have blazing fast and very well scaled out reads and writes. And then as soon as you try to do something like a snapshot or a LUN reset, it's going to get really, really hard. Because if you have something, one thing serving it, it's very easy to say stop, bump your sequence number, whatever you're going to do failure handling, and then continue. So we had to do a lot of work here across both the partition and the front end layers to do coordination. As it turns out, most people have less connections than we do backend partitions, so we coordinated at the FE layer. So as an example here, if you take a snapshot, and I noted multi-protocol, we don't expose multi-protocol, but internally we use that REST layer all the time. So when you take a snapshot, we'll actually translate that into a REST request, send it to the backend, it'll hit a random FE, it'll go to the partition that hosts that, right? And then that partition is actually going to coordinate across everything that has a connection. So we actually, every time you connect, every time you do a login, we store that in a table, so we know who is hosting that. And when we have to do a snapshot, we're actually going to reach out to those FEs and we're going to say, hey, we'd like to take a snapshot. Stop your writes for a minute. Here's your new snapshot, here's your new snapshot number or version number if you want to think of it like that. And you can continue I/O once we've heard from everybody. There's some really interesting failure dynamics here. If we can't reach out to someone, we do prioritize reads and writes making progress. So we will just actually, if we can't get a hold of everyone, we will basically stop that snapshot, retry, figure out why we can't talk to one of these guys, maybe do the failure handling to move to another one, and move on. But this was a complex part of this particular piece of things, and this is complex in the cloud generally. The more you spread, the better, basically, the better kind of throughput you can get, but the worse it is when you have to do operations like this. All right, any questions on this component before I get to iSCSI? Sub-millisecond is direct drive. We're single digit millisecond. Oh, sorry. have to repeat the question. I swore I would not do that. He's asking about latencies for this particular product. So direct drive, that's our very high performance disk stack. That's sub-millisecond. This particular stack is single-digit millisecond. It depends a lot on the read-write workload, and I don't have a table handy, so don't quote me too hard, but think around, when I say single-digit, I don't mean 8 or 9, I mean closer to something like 2. Obviously, if you have really high queue depth, that's going to be a little higher, a little lower. Reads, writes are different, but that's sort of order of magnitude.
And is it installed for every reader writing how to fit your metadata separately, apart from the data, and that's like 2 hops, which would add up to the latency, and it goes like early
Hops is part of it. Actually, some of it is also the iSCSI stack, and that's no criticism at all, but it has a lot of things that were built for, it didn't assume we were going to, be making, SSD, all this other stuff that came later, right? So NVMe is actually working on addressing some of those gaps and has solved some of those. So it's a combination. Some of it is on us. We have multiple hops. Direct drive actually has more direct hops. It loses a bunch of flexibility because the client talks directly to the server, whereas here we have more abstraction, and we pay for that abstraction. But it's also components of basically running this whole iSCSI, kind of server client architecture, both sides of it. Yeah.
So, if that's to present a page, when you create this elasticity, is direct a blob. So my question would be, is it a page or a blob that you do the operation?
So the question is it a page or a blob? In Azure Storage, if you look at the REST API for blobs, we actually have 3 kinds. We have page blobs, block blobs, and append blobs. Block blobs are very badly named. They are actually the object storage primitive. Page blobs are more the disk primitives. Append blobs are a specialization of block blobs. This is more similar to page blobs. It's not page blobs directly, but it's in that vein. So page blobs, disks, iSCSI, those are the block storage primitives. So it's going to be more similar to that. Not the same, bit different. We did a lot of other stuff, right? But that abstraction.
Yeah, because when you talk about the snapshot, you can do that type of snapshot with.
Yep, we support
right?
Yep, and we support snapshots on the whole disk stack as well. So snapshots is a generic thing we support. Block blobs have a few more things. They also have things like versioning, which is different. That's not a thing because it doesn't make as much sense if you're not going to be doing overwrite. You're doing lots of little writes, so we don't have versioning. But snapshots is something we have across the stack.
Do you have to create the disk object, like when you talk about VM, when I have to create a VHD, which is a bunch of page blob. In this case, you do similarly things, or you just now you have this one, and as you're going to use it, you're going to just increase your page.
Yeah, the question is about a little bit how this is implemented relative to page blobs. So I mentioned before that we're scaling out here. Page blobs is obviously a single interface. That's just one particular thing. It's not a spread. Page blobs, there's some similarities to page blob, but there's quite some differences too. I'd say page blobs, because of what I mentioned here with the sharding, we had to rewrite a lot of that. So for example, snapshots works completely differently because obviously if we have a single point, if we have a partition layer for a snapshot for a page blob, we're just gonna take the snapshot there, right? There's no reason to build all this coordination and mess around, right? And so this is something that's pretty specialized given we have a session-based protocol, it's not REST, and we have this, kind of different mechanism. So there's some similarities. It's a similar traffic pattern that we'd expect with page blobs, similar maybe, the way we handle reads and writes and some of that, but because of the sharding, that really blew up a lot of that, so you can't really equate it with that particular thing exactly. Maybe from a customer interface perspective, but less so from a backend perspective. Okay, cool. iSCSI. All right, I mentioned before, iSCSI, old protocol about the age of me. I like iSCSI a lot. So I mentioned before, part of the reason we love this particular architecture in Azure Storage is that it is very flexible. iSCSI is very flexible. It's kind of amazing that you can take a protocol, this was initially SCSI, that was written kind of for disks in the 80s, and apply it to the cloud. That's ridiculous on the part of the protocol. There's some grungy corners of it. A lot of people have tacked stuff on. It turns out that's very useful for us because we use a lot of the bits that people tacked on in creative ways to work around some of the problems we ran into. So first things, DNS. I mentioned DNS and SLB. So how this works, and I think this works this way for a lot of regular iSCSI implementations, is you look up, for your IQN, you have a portal, it does a DNS resolution, and you get an IP back, and you connect there. Here's the problem for us. Volumes can be moved at any time between clusters. So Different storage clusters have different IPs, and that IP can change from under people. We'll continue to accept requests on the old one for some period. In rest, this would look like a keep alive, but then we expect people to re-resolve that DNS and get the new IP. This is something we have to do in the cloud. It's both for load balancing, so we can handle load and capacity spikes. If one tenant's looking busy, we're gonna move people off. We do our best to control a noisy neighbor even within a cluster, but in the end, we wanna kind of do that movement around. The second thing is decommissioning. I mentioned we started in 2011. We're not running any of the hardware we did in 2011, yet we still have all of that data. And we expect to be able to spin up a new cluster and just get rid of one of the old ones and move all of that over. And we try to do all of that without ever talking to all of the customers we have. This isn't something like my school website where they're like, oh, well, we'll be gone Wednesday night and just don't try to access your report cards, right? Works for that. It's a coordinated thing. It doesn't work when you're a cloud provider with all of the customers we have. So that's not something where we can reach out to everybody and say, okay, we'll take you down while we move everything. So we expect this to be basically as transparent as it can humanly be. It's imperfect. You'll see things like that IP change. You might see some latency while we're moving data, but we really try to make this something that is not obvious to customers. Here's the problem. We test with iSCSI initiators on Linux, Windows, and then also the VMware custom one. None of those will ever resolve that particular DNS after the first time. And why would they? There was no assumption of this when this was done. So the problem is we'll move the IP, we'll move the volume. There are connections, even if we drop them, do something more proactive, what do? Right? They'll basically, even if we kill the login, when they re-log in, they will not resolve that DNS. So this was a difficult problem for us. It turns out there was this little piece of the spec called login redirects. So what you can do on login is return a different IP that they should go to. This seems to have been designed for down paths. This is sort of a down path. It works very cleanly for us. So when we have an old cluster, we basically just put in this little redirector, we move all the data, but we leave this little bit of metadata that basically said, here's the IP of where this data has gone. Works very nicely. Not a thing in NVMe TCP. We're going to need to come up with a different solution for that.
There are other options.
There's other options, and they're mostly more administrative plane where we've gone down that particular road. We can chat. I'll get to NVMe at the end. I expect that to be the most controversial. So I have a slide at the end, and we can talk more about it. Okay, network encryption and auth. iSCSI mentioned it's older. It supports CHAP. CHAP isn't bad. If you look at, for example, NVMe TCP, they have a modified version of CHAP with all the kind of the modernized security, but the older iSCSI CHAP is kind of not great given its age. So we aren't going to go do that. We don't support it because the illusion of security is worse than simply not having it. So we just don't support CHAP because in the end, we don't want people to only set that up and think that that is going to be okay. So we've focused on using network auth. Azure has 2 network primitives already, VNet and private endpoint. And we do our authentication via these particular mechanisms to make sure that it's network protected. So we'll do this as well for NVMe TCP, but we'd also like to do more on top of this. Obviously, we'd also like to have a stronger auth protocol, but it's pretty good. This is secure if you set it up correctly, and it's not misleading in any way. Encryption. iSCSI supports IPsec. IPsec isn't bad, but it's very complicated. And when we talk to customers, they don't want to set up IPsec. There's not a lot of interest there. Not a bad thing, but especially with just a diverse customer load, it's not something that we found supportable or that we had enough interest in. Not a lot of other choices, though. We've talked about doing things like, to be clear with encryption, by the way, I'm talking about encryption on the wire. We encrypt all of the data on the back end. That's taken care of. Don't worry about that. Encryption on the wire is a little bit of a different problem. We're not as worried about this because, we're doing VNet and private endpoints, so the packets are staying kind of within storage. It's not like we're going over public internet and just sending stuff in plain text, but we'd like to have encryption. That's something we're trying to provide, since I keep mentioning NVMe TCP, but it's TLS PSK. And it turns out PSK has a lot of the same management headache in terms of provisioning the keys. So the spec assumes the keys are on the boxes already. That's kind of hard, and it turns out that that is quite a bit of overhead. We're hoping we're going to get TLS with X509 certs. I understand there's some development there. We're watching that closely. If there's folks here from NVMe, we'd love to have it. We would use it. The thing with us is at least when we talked about this with NVMe folks in the past, their thing was, why are you using DNS? Turns out, they assume at least when we talked in the past, it was this assumption that DNS was not going to be the most common. We have DNS, so certs work nicely. But this is what we chatted about a couple of years ago. So we'll see. Or we'll get PSK to work. All right, finally, Cloud failure tolerance, and this is something I've noticed is quite different in cloud versus some other environments. I work with a lot of people that are from more traditional storage environments that have moved toward the cloud, and this is something that is kind of a different expectation in the cloud, almost a psychological aspect of it. There's this assumption in the cloud, nodes go up, nodes go down, whatever, right? Who cares, right? Massive failure tolerance. Some of this is for regular updates. We have to take things down and apply new software. Some of this is periodic restarts. If we start to see anything looks unhealthy for whatever reason, we're going to kill the node. Let's say we see memory growing. Maybe it's a memory leak, we'll investigate that. Maybe that node has just gotten busy because it has too many customers on it. Killing it and naturally letting it rebalance is one of the most efficient things we can do. We also have hardware and software failures, crashes, the hardware itself has issues. It's less common, but at the scale we're running, like I said, thousands of data centers, this happens all the time. And so we just kind of have this assumption that you can't really assume at any time that node isn't just going to disappear from under you. This works really cleanly for REST and HTTP. When you start to have session-based protocols, this is not so clean because that session, is a lot more work to set up, and it has a lot of state. So this was something that was more difficult, for all stateful protocols, nothing to do with iSCSI, and we see this with, actually all these problems also really are for SMB and NFS v4. Everything I've talked about here is problems in those environments, including these DNS redirection issues. But that's an issue we have to look at. So first of all, on the service side, we tune down how aggressively we'll try to restart if we see problems. There's more live side as a result that we have to do, kind of to manage the cloud. We did our best there. We also did a lot of more proactive. For example, if we know a node is going to go down for an update, we'll proactively kill the session rather than waiting for error handling to kick in, and reconnect is usually very fast. Similarly, we have the client side tune it to be very fast. We say try very quickly if we've killed something so that you can very actively make sure that you're getting that up again. And it works pretty well. But customers sometimes get confused and they still see those disconnects in their logs. We've tuned it down a lot. Right? But you're going to see it more in an environment where you control updates, you control node restarts, and that is a lot less common. Pros and cons, there's nothing bad about that other approach, but this is kind of how the cloud operates and something that you kind of have to take into account. Like I said, all session-based protocols we have these sort of issues for us to look at. NVMe TCB combined with the SLB using random FEs, this is very difficult to support in NVMe for a bunch of reasons because the failure handling is quite different than iSCSI with the way connections were done. So that's another beast. With there, I have a couple more slides on NVMe, but I wanted to pause and try to check where we are on time before we continue and answer any questions we have right now. Okay, go ahead.
So from the client side, when you spin up, do you already push all your iSCSI configurations that are needed, or does the customer need to do it?
Yeah, so there's some customer configuration needed. We're trying to change. Oh, sorry, repeat the question. I'm very bad about this. Thank you for reminding me. What happens with the iSCSI configurations on the client side? We don't control the client running the iSCSI things, and we're not going to run things for people. If we go on their VM and run stuff, that's kind of a violation, and we're very careful not to do that. That being said, we've tried to make it as easy as possible. We have a script, so when you want to mount one of these, you just run the script, and it'll apply all of those. We also have documentation on why we've set all these particular settings, but if you don't want to think about it, you can run the script. I wish we could do better. We're looking at ways to do better, but that's what we have right now. So we do erasure coding. Why are you doing 3 replicas as opposed to erasure coding? Like I mentioned, this is not a talk about stream. Stream would be a talk within itself. We do erasure coding, and that will happen here. There's pros and cons to erasure coding, as with all things. With erasure coding, if your data is relatively hot, that's going to be more expensive because there's more reconstruction, even if you store a full copy. So we do EC. That's managed heavily by the stream layer based on basically how much we see this data being accessed and a bunch of other policies, how much we need space on that particular cluster. But there is EC. That's all managed by that stream layer. I mentioned flexibility. We didn't have to think about it for this. The stream layer already does EC and already has those policies set up, so it's not something we had to tune at all for this project.
Yeah, there's a really good white paper for C, but that goes on the three copies, and then you EC later when the data is at rest or it's colder, so you
Yes.
have EC. But it's within the hours.
Actually, SDC had a presentation by Cheng Wang.
Oh yeah, okay, Cheng did all of that for us. Perfect. So you go watch Cheng's presentation.
Based on the
Cheng is a PhD. He's a very smart man, and he knows a lot more about EC than I do, so I do not want to butcher whatever he would say. Go watch that. Cheng has an excellent presentation.
2015, something.
Okay.
Yeah.
It's like 1014 MRC.
Yeah, but I mean, like I mentioned, he's mentioning that this was, maybe about 10 years ago. I mentioned this architecture we've been using for a lot of that time. A lot of that is probably still there. EC, I think we've evolved it. We've made things more efficient. It's not that we haven't changed things, but a lot of what he said probably in 2015 would still apply, and it's still probably very similar to how we run things. Okay, we have time. Go ahead.
You said something that sounded kind of scary, which sounded like you were doing some vendor-specific uses of certain fields, maybe through protocol.
There's not anything vendor-specific we've done. Oh, it's like, dang it, I'm so bad about that. It's asking about vendor-specific fields. We have not done vendor-specific fields for this. This was in the spec already. Because the thing for us is we want to work with off-the-shelf initiators. We don't own the initiators. We want standard Linux, standard Windows, standard VMware to work. There's some things we actually had to do for VMware that were pretty butchery, but we tried not to do anything that wasn't already there. There's a couple things we did for along that particular vein in the VMware sphere, but the Linux and Windows works completely out of the box with all of this, and we really, really wanted that to be true. So we've avoided that heavily.
Okay, so interoperability to other
Yes.
companies' products was the goal.
It was a huge goal. The main reason we did this is that we wanted to work with other things. The goal of picking iSCSI, despite it being an older protocol with some warts, as with all things, right, is that we wanted it to work with other things, and that was a huge priority here. So we were very careful we test with Linux and Windows. That is part of our default testing environment, and we do really aggressive integration testing with those.
Did anybody try to do a Windows clustering using elasticity since you're...
The question is, did anyone try to do Windows clustering with elasticsearch? I don't know, probably. Customers do all sorts of things. I don't control what they do. That's the miracle of the cloud too. I have no idea. We have a lot of people and they do a lot of creative things.
I've talked with some of my support guys that I know over there, because that would be fun.
I'd take a bet it would work because, as was highlighted, the interop is going to be very heavy, so if it supports iSCSI, it will work. The question is Windows clustering, if I didn't frame that yet.
More slides.
Oh, more slide. Okay, we have one more question, and then I want to get to the controversial portion. One more question. Sorry, I didn't catch the question. Can you repeat? It's just.
Number of CPU or my virtual machine in Azure Cloud and throughput of iSCSI.
Oh, the question is dependency on the number of CPUs. Obviously, more CPUs will go somewhat faster, but we don't have a dependency. iSCSI will work on all ranges of VMs. It'll work on small ones. It'll work on big ones. If you have more CPUs, sometimes things may go a little bit faster, but there's no problem there. iSCSI should work just fine on your smaller VMs. Okay. All right, how many minutes do we have here? Very few. So this is a very dense slide. Apologies. I tried to split it, but then I kept realizing I was missing context.
By the way, you could run a little long because people can go to lunch if they want.
Excellent. Or they can sit here and argue with me about NVMe. I love arguing about NVMe. So feel free to stay and argue with me about NVMe.
Take your time.
Okay, so NVMe TCP, I mentioned we have this multi-headed target in SLB. Now let me get into this. This gets very deep, and this is very hard to do without a whiteboard. So the top diagram I have here is just a very boiled down diagram of how NVMe works. So I mentioned iSCSI. iSCSI has a bunch of connections. Those connections are all created equal. For NVMe, it's a more layered architecture, right? We have not only, we have the subsystem, the words are different, right? But all connections are not created equal. You have this admin queue pair. That's where you're going to do things like heart beating and kind of, the initial, anything that doesn't, basically I/O is going to happen on that. And then you basically have your queue pairs that are doing I/O. Those are housed within a controller, and you can have multiple controllers within a subsystem. And so you have this much more layered architecture. The interesting thing is that the admin is very tightly coupled to its, data queue pairs, right? So you have an admin, you have those. If one goes down, they all go down. So I'll make one note here. Yes, but let's put it this way. There's the spec and there's what people have done. We tested with Linux and SPDK, and on average, we're taking the merger of what the spec says and what people practically did. And this is what we did for iSCSI as well. So practically what happens right now in Linux and SPDK is that if one of these goes down, the entire controller will go down. This is difficult when you have random connection spreading. So if you, in this diagram, for example, you have an admin that's running on one FE, and then you have 2 queue pairs, those are running on completely different FEs, you're much more exposed to failure. And it's hard for us to fix that because we have this SLB that's supposed to be for load balancing. The intention of this very clearly in the spec is that a controller runs on one machine, and we get that, but it's very hard for us to resolve that with the architecture we have. So that's the first problem. That one may be surmountable. We can go rewrite the load balancer. But traditionally, the load balancer didn't delve into looking at packets, and so that is a big shift. It's not something where we can extend something there. The load balancer is pretty mindless. It's just going to pick something. There's complexity in it in other ways around heartbeating, when nodes go down, consistent hashing. There's a lot of pieces there, but it really hasn't gone into kind of that packet inspection where we can route to one machine. We're looking in some ways to do that with ports, where, for example, we open multiple ports, and then we say, for a particular controller, make sure you're hooking it up with that port. But it's ugly because now we have a lot of ports. So, no promises on how we'll do that. We haven't released NVMe on TCP, but this is the kind of stuff we're trying, to surmount. Next, we have different problems with error handling. So I have this diagram at the bottom. You should recognize this. TS is our partition layer. If you see that mixed up in a diagram, that's the internal name. Similar to stamp cluster tenant, partition server is actually called a table server internally, so you're going to see that particular piece there. Let's say a connect, this is at the controller level. We're not getting into queue pairs. We're just going to talk about the controller level. So you get to connect on FE1, you get to connect on FE2. These are 2 different controllers. The way failover works is that you're going to retry I/O if you have an issue with an I/O on one controller onto a different controller. So that particular piece gets done. The difference is with iSCSI, before you do that retry, you're going to do an abort or a LUN reset. Linux tries, see the time there. For iSCSI, for example, that one actually does an abort and a LUN reset. Windows just does a LUN reset in iSCSI, but there's always that particular fence that happens before that retry happens. That is not what's happening in Linux and SPDK. It'll retry without any particular fencing.
That's because Linux is broken.
Yes, but we have to support it. Comment is Linux is broken, but the problem we have here is this is a massive problem with data corruption. So I think this is a known issue, but we can't release a product that has this sort of thing, and we have repro'd this live. Basically what we do is we just hang a thread on one, we let it retry on the other, we let the other one commence, and we've corrupted data. So this is absolutely hosing us in terms of being able to release this. And there's, again, some things we're trying to do to fix it. Most of them result in downtime. So basically, we'll do things where if we see something come in, it's hard to handle though. Basically, you can do a much harder reset when you see these things happening, but then you're gonna have basically everything go down, which breaks the purpose of having controllers in queue pairs. The other problem is even, for example, when a connect dies and a new connect comes in, you don't get information on where the connect is coming from. You can use things like static controllers, but those aren't supported. Linux and SPDK support dynamic controllers, and when you see a reconnect, they're not actually telling what they're trying to reconnect to. I can't tell the difference between an old connection and a new connection, and so I can't do fencing. If I knew when we were, doing a reconnect that it had basically that same label, that I knew it was trying to reconnect on this, for this other connection, I could say fence everything on that older connection, but it's not what happens, and so it's difficult to surmount that way.
But you also have a bigger problem where you can retry the I/O on an existing connection.
Yep. Exactly, and so that's why there's multiple layers of this, where even if we fix one thing, we just run into the next problem. So even if we fix the retry issue between controllers, we'll then just have the problem where basically the controller reconnect is busted. And so this particular error handling is what's kind of causing us to have difficulties with NVMe. iSCSI, we kept running into problems, and we'd find a little valve somewhere in that spec that could save us, and we have not been able to find that particular valve in NVMe. So we like NVMe, we want to support NVMe, we support, kind of getting it to work for us, but this is the problem that we've been running into with that. All right, questions? That's a complex bit.
I'm working on that problem. We published the update to the spec. It's part of the spec as of 2.3 this last summer, and that was the work that I did. I certainly talked about it.
The comment is there's someone here working on the spec on this problem, which is why we come to these conferences. But the newer specs have some solutions to this. We need Linux and SPDK and all these other folks to pick that up. Yes. So that's kind of where we are, because practically we support what's on the market. But I would love if that happens. It would make us very happy.
He has been peeling that onion for some time.
Well, aren't you proud? We noticed it. We appreciate your work. Okay, go ahead.
How complex would be tying multiple queue pairs to the same FE?
It's very complex because of load balancing. That's why I mentioned when you have a load balancer, how most load balancers work, not just ours, right, is they're going to pick something largely random underneath. They're not doing packet inspection because that is very slow. And who knows what to impact? There's 20 different protocols flowing through this. Like I mentioned, it's not even just, SCSI running on here. Half the packets are not connect packets, right? Like it's very difficult to save that, at that load balancing layer. Again, there's things we're looking at. I mentioned things like ports. You can basically say, and we can't do this at a whole layer. We have hundreds of FEs. I can't open a port per FE. But if you say basically this controller should connect to a particular port, you can do something like that. Because you can basically say there's very few nodes under that particular piece of things. So that would be one solution. There's about 20 others, so don't tie me to that particular piece. There's workarounds. They're not super great. And this is something that other clouds will run into too. Load balancers are a very generic, piece of clouds.
Yeah, going back to that load balancing on per connection instead of per controller, that is a problem that you will need to solve because it is, the heart beating is tied to the controller. And it does rely on connectivity from the beginning to the end.
Yep, and we've looked at other ways to do that. Basically I mentioned we have, ways of doing basically coordination. When I went over snapshot, we actually can solve that because we have ways to coordinate even across these disparate nodes, but it's uglier. And you end up with a lot more complex failure handling because if one node goes down a queue pair and the admin one doesn't, it's not great. I will say as a counter commentary, things all the time will be heartbeating and be down. And I've seen this a million times in the cloud where, for example, you'll have a thread be completely stuck, but the heartbeat thread is just, oh yeah, everything's cool and dandy. Yeah. So I have questions on whether this is a totally great architecture, even for single box. The cloud is a whole other level, I get that, but even on single box, it's very easy to end up in cases where heartbeat is working and the rest of it is not. So something to consider.
And the solution went in the other direction, so that, I've seen that.
Yeah, so we've all been there. Okay. Other questions? Okay, cool. Catch me afterwards. I love NVMe, I love iSCSI, and I would love to talk to you. Thank you.